All right, so continuing through chapter P here. Next little thing here we're going to get into is dealing with radicals and rational exponents. But before we do that, we're going to work on scientific notation here from the last lesson. So remember, we're going to put the decimal after the first non-zero number. So 3.497. And then we forget about the rest of the zeros. There's no other non-zero number in here. So all of these can be dropped. Times 10, and now we're looking at how many times did we move the decimal to put it after the 3. Well, 3, 6, 9, 12, 13 times. And because we were bigger than 1, it's going to be a positive exponent. So there's our number. So radicals are just a fancy way of saying roots. So typically we deal with the square root. So the square root is, so if we have a number squared and that equals a, its root would equal the radical here, a. So in other words, your square root of a is what number was times itself to get that number. So the whole thing is called a radical expression. The radical part is the root deal, the root sign, and then a is your radicand. So the number inside radicand. So if we evaluate these following roots, so square root of 64, what was times by 60? What times by itself to get 64? Well, 8 was. What about the negative root of 49? Well, square root of 49 would be 7, and the negative root would be negative 7. Square root of 1/4, well, would be a half. Now, square root of 9 plus 16, we can add them together. 9 plus 16 would be the square root of 25, which equals 5. But if they're separate, we would do the square root of 9, which is 3, plus square root of 16, which is 4, and we would get 7. So, notice how it's different if they're both under versus if they're separate when you add them. Now we have a square root, or negative underneath the square root. Well, square root of 25 would be 5. When we have a negative under here, it goes to I. Now, technically, back up here, it didn't specify whether positive or negative. So this should have a plus or minus when you do the square root, because it could be a negative 8, because negative 8 squared would give you 64, as well as 8 squared. Here it specified we want the negative root. So that's all we have to put. Here it didn't specify, so plus or minus. This here should be a plus or minus. This here should be plus or minus, plus or minus. And here it would be plus or minus, because it wasn't on outside. So does a couple things. This technically becomes 4 different answers. So if we have positive 3 and positive 4, we get 7. If it's negative 3 and negative 4, we get negative 7. Positive 3, negative 4 is negative 1. Negative 3, positive 4 would be a positive 1. So that kind of changes it quite a bit. So always remember when we're doing a square root, unless it specifies. So if it would have did the plus 64, then we want just the positive. But if it doesn't specify, we really need a plus or minus there. Now, if we have a number squared under there and then square root, then it will always be the absolute value. So it will always be positive then, because that squaring makes it positive, and then the root back sort of thing there kind of cancel each other out. Now, we have certain products or certain properties, just like we did with with exponents last lesson, where that we can follow here with roots. So first, the product rule. Now, it didn't work when we added, and it won't work when we subtract. However, if we multiply the two numbers under a square root, it will be the same as if we separate them and then multiply them. Or if they're separate and multiply, we can put them together. So that allows us to simplify square roots. Because what we could do is we could rewrite this as the square root of 5 times the square root of 100. Well, 5 we can't do anything with, but square root of 100 would be 10. So 10 square roots of 5 is how we can simplify that down. The other way to look at that is if we just do the factor tree of 5 and 100, which goes to 10 and 10. Well, 10 has extra buddies, so we can pull the 10 out. The 5 has to stay. Same thing with square roots when we divide. So here we can separate this to make it the square root of 100 over the square root of 9, which is easier to do. We know, hey, the square root of 100 is 10, we know the square root of 9 is 9. Okay. Now, in order to add or subtract these radicals, the base must be the same. So it's just like if it was an x. If it was 7x plus 5x, we'd add them and get 12x. Well, same thing here. The square roots have to be the same, so they both have to be square root of 2. So if I have 7 of them and I add 5 of them, I have 12 square roots of 2. Now, if they're not the same, you always want to look and see, can I make them the same? Well, 12 would break down to 3 and 4, which goes to 2 and 2. So we have a set here, so we could rewrite this as 7 square root of 3 plus 2 square root of 3, because the 3 would be left over, and we could pull a 2 out. So now we can say, oh, that's 9 square root of 3. Okay. Now, can we have a radical in the denominator? Actually, no, we can't. So what we do is we call it rationalizing the denominator. So what happens if we have a square root in the bottom? We're going to take the top and bottom by that square root. Because technically square root of 3 over square root of 3 is 1, and timesing by 1 doesn't change its value. That's why we're allowed to do that. So then we go straight across. So 1 times square root of 3 is square root of 3. Square root of 3 times square root of 3 is technically square root of 9, which is 3. So now that square root's gone off the bottom, it's moved to the top, and now we're good to go. So if we rationalize this denominator, we would take it times the square root of 6 over the square root of 6. So on top, 15 times square root of 6 would be 15 square root of 6. Bottom, square root of 6 times square root of 6 is square root of 36, which is just 6. Now, always look and see if you can reduce. Like here we can divide this by 3 and get 2, divide this by 3 and get 5. So we end up with 5 square root of 6 over 2. Now, that's just if it's a single square on the bottom. If we have two terms of a square root on the bottom, we have to use the conjugate, which is basically the sum and difference of the same two terms. So we use the conjugate to rationalize when we have a binomial type of a situation on the bottom here. So we would take this times its conjugate of 5 minus the square root of 3 over 5 minus the square root of 3. So up top we distribute the 7. So we get 35 minus 7 square root of 3. Now on the bottom we would FOIL this, and 5 and 5 would make 25. 5 and a negative square root of 3 would be a negative 5 square root of 3. Square root of 3 times 5 would be a plus 5 square root of 3. And then square root of 3 times a negative square root of 3 would be a minus 3. Because it would be a minus square root of 9. Move it over a little bit. So minus the square root of 9, which is 3. Now, what you notice here is this being minus, this being plus, these two cancel out. So what we have here is 35 minus 7 square root of 3 over 25 minus 3. So because it's timesing by its conjugate, the middles will always cancel. So really all you have to do is take the first times each other and then minus the last times each other, because you're going to get a negative here. So positive times a negative will be a minus for the last one. And then we can simplify this to 35 minus 7 square root of 3 over 22. Now, if we start getting into more complex radicals here, So if we get to the nth root of a real number, so it could be the cubic root, the fourth root, the fifth root, whatever, all that's saying is that's how many times the number was times itself in order to get that one. So if it's the third root, what number was times itself 3 times in order to get that? Like the cubic root of 125 would be 5, because we would take 5 times 5 times 5 to get that. Fifth root would be what number times itself 5 times. You know, whatever that is, that's how many times it would be times itself. So nth roots here. Now, if n is odd, so if it's a cube, the fifth, the seventh, it's going to be whatever sign it is in here. So if this is a negative 125, the cubic root would be negative 5. It's going to be the same sign. If it's even, it's always going to be the absolute value. So if it's to the 12th, to the 16th, whatever it is, when we pull it out, it'll always be positive. So for example here, if we have the cubic root of 8, that's the same thing as saying if we have the cubic root of 2 to the third, well, 2 is taking it times itself 3 times, so we get 2 for an answer of the cubic root of 8. Now, product and quotient works the same way with these nth roots as well. So if they're under the square root and they're multiplied, you can separate them and each give them that root. If they're divided under the same root, you can split them and get that as well. So, cubic root of 24. So this is where you're going to want a factor tree. So we can break this up to 4 and 6, which goes to 2 and 2, 2 and 3. So in this case, this is telling you how many have to group together in order to pull one out. Well, we have 3 exabuddies here with the 2. So we could pull a 2 out front, the 3 would have to stay, and so it would stay under the cubic root. So 2 cubic roots of 3 is how we could simplify that. Here, if we separate this, we would get the 4th root of 81 over the 4th root of 16. Well, what times itself? Okay, let me do this. Let's go 81 here, which would go to 9 and 9, which goes to 3 and 3, 3 and 3. 16, which would go to 4 and 4, which goes to 2 and 2, 2 and 2. So 3 is times itself 4 times, so this top is going to go to a 3. 2 is times itself 4 times, so the bottom is going to go to a 2. So whatever number is here, that's how many factors there has to be in order to pull one out. So 4 factors, so 1, 2, 3, 4, pull the 3 out. 1, 2, 3, 4, pull the 2 out. So I like to call them exabuddies based off of Finding Nemo. When they get off the trans-Australian current, he always says find your exabuddy. Well, on a square root, you need 2. So 2 exabuddies together. Here, 4th root, we need 4 of them. Now, just like square roots, we can add and subtract these. However, we have to have the same. So for 16 here, I would break this down to 4 and 4, which goes to 2 and 2, 2 and 2. So it's cubic root. We want 3 of them, and we'll have 1 left over. So what we're going to have here is, so 5, and then you'd pull out a 2, cubic root of, and there'd be a 2 left over, minus 11, cubic root of 2. Well, pulling that factor out, you're going to times by whatever's in front of the square root, or the cubic root in this case. Whatever's in front of that root, you're going to times when you pull that factor out. So this here is really 10 cubic roots of 2 when we pull this 2 out. So 10 of them, and I subtract 11 of them, I'd end up with a negative cubic root of 2. Now, something to keep in mind, the square root of a is really saying a to the 1/2 power. So what we're going to get into is some fractional exponents. So, whatever the nth root is, it's going to be 1 over n. So if it's the 1/3, this is really saying the cubic root of 125. Now, it had a negative, so that would move it to the bottom. which means we're going to get which 125 goes to 5 and 25, which is 5 and 5. So you have 3 of them here. So it's going to go to 1 over 5. For 64, again, we would flip it. We'd have 1 over the cubic root of 64, which goes to 8 and 8, which would go to 2 and 4, 2 and 4, which goes to 2 and 2, 2 and 2. So here we're going to have 1 set, 2 sets. So this would end up being 1 over 4 then, because we'd have 2 times 2. So as far as those fractionals go, it doesn't always have to just be a 1 on top. We can have whatever power to the top, the root will always go to the bottom. So if it is, say, a to the 2/3, that'd be saying the third root, a squared. Now notice how we can write it 2 ways. We can either write it to the roots, to that exponent, or that exponent underneath that root. Either way works. So to simplify these, to me, I like to tear it down and then build it up. It's a lot easier than building it up and then trying to tear it down. So I would write this as the cubic root of 27 squared. Well, cubic root of 27, 27 goes to 3 and 9, which goes to 3 and 3, would be 3 inside there, and it's squared, which gives me 9. To me, that's easier to do than trying to square 27 and then trying to find the cubic root of that. But that's just me. Now, if we have division going on here, so we still divide these, so 32 divided by 16 is 2. Same base, remember what from exponents before, if it's the same base, we subtract, so 5/3 minus 3/4. So common denominator would be over 12. So 4 would make this 20, and 3 would make this 9, which leaves with 11/12. So our new x would be x over 11/12. So remember, if you're dividing, you subtract the exponents. If we're multiplying, we add the exponents. But just because they're fractions doesn't mean you still can't do that. Now, what happens here? Well, here we can go backwards and put them back together. So we would have x, the top is the power, the bottom is the root. Well, 3/9 we can rewrite as x to the 1/3, which we could write as a cubic root then of x to simplify that down. So just because it's like, well, we don't have 9 of them in here, doesn't mean we can't reduce this and simplify it a little bit here. Now that's it. That's it for this lesson. So any questions, comments, concerns, you can pan me, email me, send me a message on Google Classroom. Remember, you can always pause and write stuff down or rewind if you need to hear it again. Otherwise, until next time, we'll talk to you later.